Okay, so here we're starting the second topic of chapter 14 or unit 5, which is all about the rate law. So if you go through, read those essential knowledge prompts, and they will sort of give you a clue as to what is the most important part of this particular topic. And one of the things that we are going to be looking at especially is determining or writing a rate law. Well, what is a rate law? So you can see by the definition down there that the rate law is a mathematical expression, an equation that relates rate to the initial concentrations of each reactant. And if you look at this table for that particular balanced chemical equation, you can see that yes, if I change the initial concentrations, I do change the rate of the reaction. And what the rate law is going to do is provide more information on that, provide a mathematical relationship so that I can predict if the initial concentrations are X and Y, what will the initial rate be? So these are, how do we get rate laws? These are determined experimentally. What that means is that we're going to need to actually look at experimental data like the data table on the previous slide in order to determine the rate law. So you can see what is the general format of these. So its rate is going to be what we're solving for. So that's equals. There's this thing called a K. It's called the rate constant. It's a lowercase k, not a capital K. A capital K will be something else. And then it's, in brackets. So what does that mean? The concentration. So that means the concentration of the reactant. And what changes is going to be the exponent on that rate law. And also if sometimes both reactants aren't even in it. If you think of the units of these, rate is always going to be in molarity per seconds. Concentration would be in molarity, but the superscripts or the exponents are going to come into play. And that means that K is going to have some really strange exponents. Or excuse me, not exponents. K is going to have some strange units with it. So just some vocabulary to get down. When we say the reaction order, what are we saying? What is that word referring to? It's referring to the exponents. So for instance, if I say the reaction order with respect to NO2 is 1, that means the exponent on NO2 is 1. If I say the reaction order with respect to O2 is 3, that means the exponent on O2 is 3. And the terminology, what is the overall reaction order? All that means is the sum of the exponents. You just add them up. So let's actually do some practice with figuring out what would be the unit of the rate constant if this is the rate law. Rate equals K times the concentration of N2O5 to the first power. So if I just bring this over here in the middle, what would be the unit of the rate? Rate is molarity per second. I don't know what K would be, but the unit of N2O5, the concentration of N2O5 would be molarity. So now I'm just going to do the algebra. I'm just going to isolate K with just the units, divide both sides by M. And when I divide a fraction, it's like multiplying by the reciprocal. We're going to use that for a lot of these problems. So it would be molarity per second times 1 over molarity, multiplying by the reciprocal. Notice what happens, molarities cancel. So what is the unit of K? It's just inverse seconds. You might also see this as seconds to the -1. Those two things mean the same thing. I will try and refrain from printing an S, right? Anytime that we use seconds in chemistry, we try to put it as the cursive just because a lowercase s in printing can look like a 5. So we try to make sure that that is clear. Here's a little same thing. We're going to do the same thing again, but a more difficult, more complicated rate law. Rate equals K times the concentration of CHCl3 times the concentration of Cl2 raised to the 1/2 power. The unit of rate is always molarity per second. I want to solve for what would be the unit of K. The concentration of CH3Cl would be molarity. The concentration of Cl2 would be molarity raised to the 1/2 power. When I multiply two quantities that have the same base, I add the exponents. Molarity per second equals K molarity. You can do this as 1.5. You could do it as 1 and 1/2. You could do it as 3/2. They all the same number. Divide both sides. Multiply by the reciprocal. And now look at what happens. The molarity on the top cancels out with one of the molarities on the bottom. So my K is equal to molarity to the 1/2 or 0.5 times seconds. Very weird units. We could also think of this as seconds -1, molarity -0.5. Two different ways of writing the exact same thing. Now, let's actually, put it all together. Now that we kind of have an idea about what a rate constant is going to look like, rate equals K times the concentration of the reactants raised to some exponent. How do we figure out what those exponents are? Remember, we've said they need to be determined experimentally. How do we do that? So here's a typical problem. It's A plus B yields C. And if I look at the experiment, I've done this experiment 3 times and I have 3 different initial rates. Just like in any good science experiment, we have kept one of the variables constant and we've changed the other one. So sometimes if you look at 2 experiments, A is kept constant, sometimes B is kept constant. I want to find the exponents on those. I know it's going to be rate equals K times the concentration of A raised to some exponent times the concentration of B raised to some exponent. I'm going to figure out what those numbers are. Let's look first at just changing A, which means I have to look at what experiments is B kept constant. And if I look, B is kept constant in experiments 1 and 3. What have I done to A? I have doubled A. So think about this, right? Rate equals K is going to always be the same times the concentration of A raised to some power. I'm going to leave B off because B is constant. What has happened to the rate? The rate has increased by a power or by a factor of 4. Don't worry about K. What has happened to... I put a 0 here. I didn't mean to put a 0 there. I meant to put an M. What has happened to A? Well, concentration of A is doubled. So then what was the exponent there? The exponent there must have been 2, right? If I think about, sometimes I'll put a box here and think, what number would go in there to make that equation true? And it would be 2. Great, so what I've just found is that rate equals K times the concentration of A squared. And I'm going to do the exact same thing, but with B. What experiments do I keep A constant so that I'm just looking at B? And that is experiments 1 and 2. So rate equals K times the concentration of B raised to some power. What happens to the rate? The rate is multiplied by 1. What did I do to B? Well, I doubled it. So then 2 to what power is 1? That's 0, right? That anything to the 0 power is equal to 1. So that must mean that this would be the concentration of B raised to the 0 power. But honestly, we don't even write that in to the rate law. So we just say the rate equals K times the concentration of A squared. What that means is that the concentration of B does not factor into the initial rate. We'll look at why that could be in a little later on. So now now that I have the equation, now I'm just substituting for different variables. The next thing I want to find is the actual rate constant. So I know rate equals K times the concentration of A squared. I can use either the data from experiments 1, 2, or 3. I always just choose whichever one is the easiest numbers. That looks like experiment 1. So 4.0 times 10 to negative 5 molarity per second equals K. The concentration of A is 0.100 molarity squared. Square it, divide. My answer comes out to be 4.0 times 10 to the negative 3. And if you, this is where you may want to, off to the side here, do out the units of the rate law. So it would be a molarity per second, and then I would divide it by a molarity squared. That's the same thing as molarity per second times 1 over molarity squared. One of those molarities cancel. So the unit of the rate constant is molarity times seconds on the bottom on the numerator, on the denominator. And then the last question is, what is the rate of the reaction when A is 0.05 and B is 1.10? I now write the rate law, but this time actually writing in the rate constant. 4.0 times 10 to negative 3, 1 over molarity times seconds. And that would be times the concentration of A squared. I know the concentration of A, substitute that in. Right? Multiply, do that out, and I get 1.0 times 10 to negative 5. Think about what happens to the units here. 1 over molarity times seconds times a molarity squared. One of these molarities cancels out with one of that molarity. So this would be molarity on top and seconds on the bottom. And since you're solving for rate, that's exactly what you want. Now, pause the recording here, go ahead and work on this problem on your own, and then unpause and check your answers. And if you didn't get them right, then go back and listen to me going through them again. Right? So to determine the rate law, I'm going to look at holding H2 constant. What happens when I double the concentration? So when I double the concentration, what happens to the rate? The rate gets multiplied by 4. So that means that the exponent on the NO is 2. What happens in experiments 1 and 2? When I double the H2, I double the rate. So that means that the exponent on the H2 is 1. Now, calculate the value of the rate constant. Rate equals K times the concentration of the NO squared times the concentration of H2. I'll just use the first If I do this out, 1.23, the units are molarity squared times seconds for K. And now plug everything back in. Right, times the concentration of NO squared times the concentration of H2. So 0.050 molarity squared times the concentration of H2, 0.150 molarity. I would have the units of my answer would be 1 over molarity squared seconds times molarity cubed, right? One of those cancels, or two of those cancels out. My answer is 4.6 times 10 to negative 4 molarity per second.